Okay, here's a review for the Unit 8 Gas Laws, Part 2, with number 11. This is going to go fast. A gas at 300 Kelvin occupies 6.5 liters. What will its volume be? There's no discussion of pressure, so it is going to be Charles' law. V1 over T1 is equal to V2 over T2. The P1 and the P2 end up getting canceled out because there's no discussion of pressure. Therefore, we can assume it doesn't change. You don't have to remember Charles' law. You just need to know that it is a direct relationship. When you have something on the top and the bottom, or numerator and denominator, it has a direct relationship. So we would expect with this decrease in temperature for the volume to also decrease. So we're solving for V2, multiply both sides of the equation by T2. So V2 is T2 times V1 divided by T1. So that will look like 250, 5 in there, Kelvin. And the original volume was 6.5 liters divided by the original temperature, which was a 300 Kelvin. Kelvins cancel, we're left with liters. We do the math and it comes out to, with 3 significant figures, 5.42 liters. Number 12, we're looking at a partial pressure problem. Total pressure is just literally the 3 of them added together, and you get 99.68 kilopascal. Number 13. Let's see. Partial pressure problem. But it's worded a little bit different, so it takes a little bit of talking about. You have a sample of nitrogen gas, and it's in this volume of a container. Gases always have whatever volume the container they're in. And the pressure is 88.3. If you're placed into the same sized container again, you still have that same pressure. It doesn't change. It already holds hydrogen gas at a certain pressure, but regardless, the partial pressure in the new container is what it came in with, or that 88.3 kilopascals. So that's the answer for the first part. What is the partial pressure of the nitrogen? It's still this. Same as what it came in with. Again, why are we making that assumption? Because of the size of the container is equivalent. They're saying it's equal. So at the same volume, it'll still occupy that same, or still have that same amount of pressure. And then what's the total pressure? You literally now can add them together. That's all. So the 125.6 plus the 88.3 is 213. So it's a confusing sounding problem, but the concept is relatively simple. Because they're going into the same size container together, they each contribute their original pressures, and the pressure is now the 2 of them added together. Number 14. Let's see, it is a combined gas problem. P1, V1, T1 is equal to P2, V2, T2. That's a 2. Nothing gets crossed out. Nothing is staying constant. You're told that there is a new pressure and a new temperature, and you're asked for a new volume. You need all 6 of these. And the volume that we're solving for is this V2. How do we get V2 alone? I'm going to multiply both sides of the equation by T2. And I'm going to divide both sides of the equation by P2. Or you can cross multiply and divide if algebraically that feels more comfortable. That is equivalent. But regardless of what way you do it, you discover that V2 is equal to T2 P1 V1 divided by P2 V2. All you have to be certain of as you implement that equation now is that your temperatures are in Kelvin. That's not an option. your pressures match, which they do, so you can use them. They don't have to be converted to anything else. And you end up with those 3 in the numerator, those 2 in the denominator. And just for the sake of time, I will just give you the answer, 50.4 milliliters. Why is it milliliters? Because you put milliliters in. If you're going to put milliliters in for V1, you're going to get milliliters back out for V2. If you were told, which you weren't, but if you were told that the answer had to be given in liters, then you would convert. Or if it was multiple choice and all of your choices were in liters, then you would convert. A liter is 1,000 milliliters, so you would end up dividing, and it would be this many liters. That was not a requirement for this question. I'm just showing you just in case you had to do some conversions. That's what would happen. Number 15, gas collected on a certain day at a certain pressure had this volume. A day later, the volume changed. What was the new atmospheric pressure? There's no discussion of temperature, so there's changes, so it's the combined. No discussion of temperature at all, so you kind of have no choice. You have to assume then that the temperature did not change. You have nothing to work with. So we're going on the assumption that temperature is gone. If you knew a temperature, it wouldn't matter, it wouldn't change. If you put them in, fine, but it wouldn't change what your answer is going to be. Turns out to be Boyle's law. And remember, this means when you've got 2 variables that are being multiplied together, that is the classic inverse relationship. As one goes up, the other goes down. If one goes down, the other one would go up. So if you look at our problem here and figure it out theoretically before we even actually do a calculation, if our volume's going down, then we would expect it is because our pressure went up. And that's a way of checking yourself too. That's the advantage of knowing theoretically what is supposed to happen. Atmospheric pressure on the second day means P2. We're solving for P2. So I'm going to divide both sides by V2. Or in the cleaned up version, it means that P2 is equal to P1 over V1 divided by V2. You put all of those in. You can use the volumes in milliliters. That is fine because it's just a simple ratio. And your P2 is going to calculate out to be 1.15 atmospheres. And then go back and do the little double check. Is that what you expected? Our volume went down, so we expected an increase in pressure, which indeed happened. And that inverse relationship that is always expressed with 2 variables being multiplied together, 2 different variables, that indeed, that is what we expected to have happen. Just a little drop in volume because of a little increase in pressure. What Celsius temperature will 11.8 moles of gas exert, blah, blah, blah. There's no discussion of a change, so no discussion of a change means we're going to use the PV equals nRT. We need our Celsius temperature, but using the pressure volume equals nRT, our temperature is going to come out in Kelvin. How do we know that? Because of the R value. If you look at the units of the R value, all the R values have a Kelvin component. So temperature is going to be equal to the pressure. The 592 kilopascals is fine to use. Our volume is already in liters, which is good. We have to use liters for PV equals nRT. Again, because of the R value. We're controlled by the R value in these PV equals nRT. And the R values, we have 3 different ones depending on our unit of pressure, but they're all solved for liters. They're all done with liters, and they're also all done with Kelvin temperatures, of course. So let's see. R value with kilopascals is the 8.314. In the units, again, clunky and awkward, yes, but get over it. kilopascals, mole, Kelvin. Lastly, oh, we didn't put in our number of moles, 11.8 moles. And then you double check. Kilopascals cancel, numerator, denominator, liters, numerator, denominator, moles, numerator of the denominator, denominator of the denominator. I know it's weird, but that's the way it goes. And Kelvin is in the denominator of the denominator, which means it becomes the numerator. And you're left with just degrees Kelvin, which is a good thing. That's what we're supposed to have because we're solving for temperature. Then you do the math, and it turns out to be 197.2 Kelvin. The question said at what Celsius temperature, so we're then going to subtract 273. That's a 3. 273.2. Oh, that's just a conversion. And it's really horrible looking. Let's see, maybe I should even erase. So our answer comes out to, I guess about negative 75 degrees Celsius. I guess we could have another significant figure in there, but you get the idea. So 197 Kelvin converted back to Celsius means you have to subtract the 273. Number 17, a sample of gas, calculate the number of moles. Okay, there's no change, it's just we don't know the moles. So PV equals nRT divided by RT on both sides. That's the way algebra works. An equation is still an equation as long as you do the same thing to both sides. So the number of moles is going to be equal to the pressure, which is 149 kilopascals, times the volume, which is 30.8 liters, divided by the R value that matches kilopascals, that is the 8.3141 again. The units are the liter, kilopascal, mole, degree Kelvin, and our temperature has got to be in Kelvin, which it already is, so don't add 273 again, just 325 Kelvin. And if you do all the math, cross off all the units, you'll get number of moles. Moles is in the everything else cancels. Kilopascals, kilopascals, liters, liters, Kelvin, Kelvin. Mole is in the denominator of the denominator, which means it's going to become the numerator. And then you do the math, and 3 significant figures, 1.70 moles. Number 18. Number 18, we need density, which is a little different. It's a little harder problem. Density is equal to mass over volume. They've given us the mass. What we don't know is the new volume. So we're actually going to use a combined gas law on this. And solved for V2, I'm kind of going fast. Solved for V2, the combined gas law will end up being P2, P1, V1 over P2 times T2. And then if you put all the numbers in, 345 Kelvin times the 108.8 kilopascals times the original volume, which is 1.88 liters, divided by the 68.3 kilopascals, which is the second pressure, the new pressure, and the original temperature is 225 Kelvin. Kelvins cancel, kilopascals cancel, we're left with liters, which is what we should get for volume, and mathematically it comes out to 4.59 liters for your second volume. Number 19. 19 is gas law stoichiometry. It's kind of a combination of Unit 7 and Unit 8 together. You're going to take your 13.5 grams of potassium chlorate times 1 mole of potassium chlorate, 122.55 grams then the mole ratio, 3 moles of oxygen, 2 moles of potassium chlorate. So this is very much Unit 7. Convert into moles, use the mole ratio from the balanced equation. And then back in Unit 7, our last conversion factor would have been 22.4 liters over 1 mole. But we're no longer at standard temperature and pressure, so we can't do that. Instead, what we're going to do is stop and actually calculate the number of moles that we got, which is 0.165. And then, after you do that, you're going to use PV equals nRT. So now that we're no longer in Unit 7, now that we're in Unit 8, we're going to take that number of moles that you get after that third conversion factor. If you watch, those will be gone. That will be gone. It should say moles. And you're left with moles of oxygen. And PV equals nRT. Divide both sides by RT. Put all of your numbers in. Oh, wait a minute, I'm sorry. I solved for N. That isn't what I meant to solve for. I meant to solve for V. My mistake. So, we're dividing by P. And there's our V. Our V is equal to nRT over P. And here's our N. We had to find our own N. There it is. R is from the packet. T is the 40 degrees converted to Kelvin. And the pressure is the 85.4 kilopascals. I don't have it actually solved, but that is how you would do it. And we'll wrap that up now.